meeting ID wrong because I did it like 2 times and it said I had the wrong ID. So,
Wow. Well,
well,
all right.
we better get down to business.
Yeah, really. What do we do? We got a lot to review, I'll bet.
Well, I have my final tomorrow.
Okay.
So, I just basically this afternoon I've just been redoing all the problems in the review packet.
Okay.
And
You narrow it down to a few that you didn't know how to do?
I can.
Okay, cool.
All right, so a few of these I look at them and I'm like, geez, why can I not do this? Because they look so simple. But I could be doing some simple mathematics mistakes. But
Okay.
Here's one. The absolute value of 7 minus 2x equals 3.
Okay. Whenever you see an absolute value equation, it always can be written as two equations. It always means two things. So our first step is to write what two things this means. And I'm going to write them horizontally. In other words, it means one thing over here or something else, and then I'm going to solve each one vertically. So what's the first thing it means?
It means 7 plus 2x equals 3?
Never change what's inside the absolute value sign.
Oh. Okay.
Never. In other words, this one is also 7 minus 2x, only in this case it's equal to minus 3.
Well, right there is where I went wrong.
Yeah.
Okay.
And then it's a simple matter to solve for x. It looks like x is going to be equal to 2 over there. And here it looks like x is going to be equal to 5, if I did my math right. Yeah. And both of those work. In other words, if you check it, 7 minus 2 times 2 is 3. And 7 minus 10 is minus 3, but the absolute value of minus 3 is 3. So, this applies whether it's an equation or an inequality. In other words, when I say it applies, I mean never change what's inside the absolute value. In other words, if it's an inequality, then the left thing is whatever's inside is greater than 3, or whatever's inside, and with an inequality, you have to turn the inequality around and change the sign. So that's going to cover all absolute value equations or inequalities. Just remember, never change what's inside the absolute value and you'll be fine, because you can't really get it wrong if you always follow that.
Never change.
Yeah, in other words, for these things here, that's always whatever is inside the thing.
All right. That makes sense. Okay, thank you. We also have oh gosh, what is it? Okay, here we go. It says solve for x, and it is 4 raised to the power of x equals 16 raised to the power of x minus 2.
Okay. Typically, this is an exponential equation. It's exponential because the variable is in the exponent. It's not on the line. Okay. So we don't have an algebraic way of solving these. So typically, this would be a logarithmic solution. But there's something that these two numbers share, 4 and 16. And that is they both have the same exponential base. In other words, I can write 16 as 4 to some power. And when I do that, I end up with 4 to the x. Well, 16 I can write as 4 squared. Always put it in parentheses. Make it to the x minus 2. Now apply your powers of exponents rules. So what would the right side become?
So when an exponent's raised to an exponent, I need to review these.
You multiply the two exponents.
Multiply.
You always do one level less than what's being done with the base.
Okay.
Let's review all of them. If I have 3 to the 4th times 3 to the 5th, I am multiplying the bases. So what would I do to the exponents?
Add them?
One level less, correct. Yeah. If I have 3 to the 5th divided by 3 squared, what would I do to the exponents?
Subtract?
Because its subtraction is one level less than division, and division is what I'm doing. So when I'm doing, you can call this exponentiation or double exponentiation. I kind of like to call it double exponentiation. I'm going to multiply. One level less than exponentiation. So when I multiply, what's the new exponent become?
4 raised to 2x minus 4.
Now, we don't need to use logarithms to solve it because I have some number raised to an exponent equals the same number raised to a different exponent, which means I can equate the exponents. And then when I solve, I get x equal 4.
Perfect.
And that works. In other words, 4 to the 4th is equal to 16 to the 4 minus 2. And that's true. 4 to the 4th power is equal to 16 squared. Okay. So when they give you a problem like this, what you're looking for is common exponential bases. Let me give you another one real quick. How am I going to solve this?
You're gonna... So you know...
Is there...
Oh, you're gonna have to...
Is there a common exponential base? Is there a common exponential base between 9 and 27?
Yeah, 3.
Yes, that's the key. It's not 9. You're not looking for common factors. You're looking to be able to represent the 9 using the same number that you're going to represent the 27. So I'm going to say 3 squared in parentheses, and the parentheses are very important because if you don't put the parentheses around it, then it's not going to work out right. Only because of this parentheses can I multiply the exponents.
Okay.
So that becomes 3 to the 2x equals 3 to the 3x plus 6. Now that I got the same base, equate the exponents, so 2x would be equal to 3x plus 6. And solve. X would be minus 6.
Awesome.
So whenever you see an exponential equation, look for a common exponential base.
All right.
Okay.
So I have another one like that, but I think it's
Go ahead.
5 raised to the 2x equals 3 raised to the x plus 1.
All right. We don't have a common exponential base here. We got to use logs to do this. You've had logs, right?
Yep. Yeah. They're a little hazy, but they're there.
Well, whenever you have to use logs, I always use natural log. If I've got to take the log of both sides, I'm going to take the natural log of both sides.
Okay.
I'll show you why. Okay? Once I take the natural log of both sides, now I can bring that exponent down on the equation line. Remember the rule that b raised to the x, the natural log of b raised to the x equals x times the natural log of b. In other words, you can always remove the exponent and bring it down in front of the log. So now that I've taken the log of both sides, I can write 2x natural log of 5, that's what this becomes, equals x plus 1 quantity natural log of 3. Now I have an algebraic equation that I can solve. That's just a number, that's just a number. Not that easy to solve. Let's go through this solution, just because it can be a little tricky. It throws people off seeing this because they tend to think of it as a variable, but it isn't. It's just a number, which means I have to distribute it.
Okay.
So the right side becomes natural log of 3 times x plus natural log of 3. So all I did was multiply natural log of 3 by both terms.
All right.
Left side becomes 2x natural log of 5. Now I'm going to gather all terms with x in them on the same side of the equation and anything without x in it on the other side. Well, I got an x there. I'm going to move it to the left. So the left now becomes 2x natural log of 5 minus x natural log of 3. The right side has just that number on it.
All right.
Now we're going to factor out x. That's always the hardest part of these, is what to do when you get to this problem. Well,
yep.
Just make sure when you factor it out that after you multiply it back together again, you get what you started with. That's always a good check to do when you're factoring something, especially in this situation. In other words, after I've factored it, make sure you redistribute it to make sure you have this, and you do. Well, on the right side is just this number. Now all I have is a coefficient in front of x, or behind it, doesn't matter. So x is going to be the natural log of 3 divided by 2 natural log of 5 minus natural log of 3. And then you don't necessarily have to do this last step, but this 2 can go as an exponent. I can take that 2 and make it 5 squared, or even say natural log of 25. So, I mean, there's lots of ways you can simplify this. I'm not sure how far down your teacher wants you to do it. I would guess that is a good answer.
Yeah, I think that would probably be fine.
And it's better than numbers or decimals, because if I put in a decimal here, it's an approximation. It's rounded off. If I leave it like this, that's precise. That is a precise number.
Okay.
Okay. And did it matter if I used natural log or common log? Not really. I could go back to the very first step and take the common log of both sides. The only difference is when I get down to this step, I'm going to have the common log of 3 divided by the common log of 25 minus the common log of 3.
Okay.
Okay. So that's why I always use natural log, is because it really doesn't matter. The one thing you probably don't want to do is take the log base 5 of both sides, or the log base 3 of both sides.
You'd have to like work that down into a decimal probably,
well,
right?
No, you would at some point have to use the change of base formula.
And we didn't learn that.
Right, so that's why it's better to just use common logs every time, I think.
Yeah.
As long as you're dealing with weird numbers like 5 and 3. If one of these numbers was e, then I would definitely use natural log. Because the natural log of e to the 2x is just 2x. That reduces immediately.
Okay.
I would just always use natural log, unless one of the numbers is 10. And then common log will get you to the answer a little bit quicker.
Because isn't the common log of 10 1?
Well, if I had, let's make the problem a little different. Let's make this 10. Now, by taking the common log of both sides, the left side immediately becomes 2x. Now I still have to deal with the right side, so I still have this. But I do get to my answer a little easier. Only because I don't have any log on the left side of the equation anymore. In other words, when you take the log base of the same number to an exponent, it's just equal to that exponent. So when this was 5, it would have been tempting to take the log base 5 of both sides. Problem is that leaves you in a problem on the right side. In other words, I could take log base 5 of both sides, and that immediately reduces the left to 2x. But now I got this problem of x plus 1 times the log base 5 of the number 3. You can't get that out of your calculator. Your calculator only has common log and natural log.
So there you're stuck.
Well, you'd have to use the change of base formula to handle that expression. So I say avoid the change of base formula entirely by just always using natural log. It makes the algebra a little harder. In other words, that algebra was a little tricky when we solved this, but not really any trickier than having to apply the change of base formula.
Okay. All right. And this is just a quick question. I just want to, sometimes I get it mixed up.
Okay.
So it says write 3 raised to the 4th equals 81 in logarithmic form.
Okay.
So is that going to become the log base 3 of 81 equals 4?
Yes. The way to memorize it, the way you'll never get it mixed up, is memorize logs are exponents. So the very first thing I can write here is the log is 4, right?
Oh, because the log, okay.
Logs are exponents. So now all I have to do is figure out where the 3 and the 81 go. And you know that base always goes down there.
Yeah.
It just leaves only one place for the 81 right there. And then if you're going the other direction, the way I memorize it is it's the number on the far left raised to the power of the number on the far right equals the number in the middle. So to go back the other way, it would be 3 to the 4th equals 81.
All right. Awesome. So,
that's why the rules for logs are basically the same as the rules for exponents. In other words, that's why the log of a times b is equal to the log of a plus the log of b. Notice that's how we handle exponents. When I'm multiplying, I add the exponents. Well, I'm multiplying, I'm adding the exponents.
Okay. Yeah, it's coming back slowly.
Well, there's a lot of material to cover in an Algebra 2 final.
Yeah.
You're really taking an Algebra 1, 2, and 3 final is what you're doing. Because there's not a lot of difference between Algebra 1, Algebra 2, and even Algebra 3.
Wow.
Now, Algebra 2 tends to cover it all, and then if you ever do take Algebra 3, it'll just be recovering the same stuff pretty much.
Yeah, that'll be a nice little review.
Yeah. Yeah, there's nothing, I mean, if you've covered conic sections and logs, you've hit the the end of algebra pretty much.
Nice. That's what you want to hear. So do you think we have time for one graphing of a absolute value?
Sure. What is it?
All right, so it asks you to graph y equals 2, absolute value x plus 2, and then close the absolute value, minus 1.
Okay. What we need to do is look at this as a transformation problem.
Okay.
So what's the elementary function? Right there.
Okay.
Okay. So if you know how to graph the elementary function, absolute values always kind of look like that. They look like a V.
Okay.
Because as x goes positive, y is positive, and as x goes negative, y is positive. Okay? So, what is being done to my elementary function to get this? There's three things that are happening. What's the consequences of that two?
Does that change the slope?
It's a vertical stretch. Okay? If I were to put a 2 in front of that, it means that any point that's there is going to be twice as high. So the net effect of that is it makes the curve look like this.
Okay.
A vertical stretch. Changes the shape of the curve. Okay? Let's handle one of these at a time. What's the effect of this plus 2 inside there?
That changes where the vertex is going to be?
It's a horizontal shift. And the standard is always x minus h. So when I see an x plus 2, it means h is minus 2, and minus means to the left. So if I was going to graph just this function, I would just take my elementary function, move it 2 units to the left, does not change the shape at all. Strictly a horizontal shift.
Okay.
Okay? And then finally, what's the effect of that?
That moves it down 1?
Correct. So I would start there, do it like that. Now, if we do all three to reflect this, I'm going to move it left 2, down 1, and vertically stretch it. And the vertical stretch is the only part of that that changes the shape. In other words, it makes it narrower. I didn't really draw it with a good vertical stretch factor. Let me redraw it.
So if you had to find the slope of that, is that just involving the number outside of the absolute value, the first number, or?
No. I see why you said that, because it looks like it's in y equal mx plus b format.
Yeah.
Actually, you're right in this case, because the slope of the regular function is 1.
Oh, okay.
And the slope of this is twice as steep. Each side is twice as steep. So in this case, that is the slope, is that number in front of the absolute value. I guess it might always be, now that I think about it. I never had really thought about it before, but yeah, I think you're right. That's always going to be the slope. In other words, if I said, what is the slope of this? It's 3.
Awesome.
Well, hold on. Let's back up one there. It's not 3. It's 3 there, but it's negative 3 here.
Oh, so you'd have to add a plus minus.
Well, yeah, exactly. In other words, you can see from the graph that one of them's positive and one of them's negative. So there's no slope to that curve because it's not a single line. There's two slopes. There's this slope and then there's this slope. and usually they're the negative of one another. So you could say that the slope of this part here is plus 2, which makes the slope of that part there minus 2.
All right. Well,
Unfortunately,
thank you very much.
Yeah, I gotta go. Otherwise, I could give you extra time. But this is my busiest day of the year, probably.
Yeah,
the day before finals, and most everybody has their final either tomorrow or Thursday. So,
oh yeah,
yeah.
almost done with school. Then you'll have a break.
Sorry for my dog barking. When it's thundering out, my dog will not shut up.
Yeah, neither does mine.
I guess that's better than going and hiding under a chair somewhere. I'm not sure.
That's true.
Whether you have to listen to it or not. But Casey, have a good one. I will talk to you again some next year, or I am running a special in the summer. I don't know if it'll interest your parents or not, but I'm offering 4 online hours for $80. In other words, only $20 a session, which is about half rate.
All right. We're going to send you a check over for
okay.
the past few sessions that we haven't paid for yet, so that'll be in the mail tomorrow.
Yeah, that's fine. I'm not worried. I'm never worried about you guys paying. But yeah, I'll send an email to you announcing this special that I'm kind of offering for June, July, and August is when this would apply.
All right.
Okay. I call it the Prevent Summer Brain Drain special, because what I repeatedly find is that when people go 3 months of summer vacation without any math, it's amazing how much of it gets drained.
It is amazing.
Yes. Every student I have that takes a summer break, and when I start working with them again in the fall, it's amazing how much they've forgotten over the summer. So, might be worth your time to do something like that.
All right. Well, we'll look into it.
All right. Thanks, Casey.
Thanks. See ya.
Have a good summer. Bye-bye.
Thanks. Bye.